गुड इवनिंग रवि।
Yeah, good evening, Rajiv ji.
आज आए नहीं क्या लोग बाग?
गुड इवनिंग।
हाँ, अभी तक तो वी आर वेटिंग।
चलिए रुक जाते हैं। अच्छा एक चीज बता रवि जी।
हाँ, बताओ।
वो जो इसकी एग्जाम्स थी वो मैं मिस कर गया, डेट निकल गई उसकी। somehow आई मिस्ड इट।
डेट रजिस्ट्रेशन की?
नहीं नहीं, जो असाइनमेंट होते हैं ना इसके
ओके।
ऑनलाइन जो पोर्टल पे,
हाँ।
असाइनमेंट की जो लास्ट डेट थी वो मिस हो गई मुझसे।
ओके।
somehow तो मैं भूल गया वो। तो तीन तीन वीक के मैं मिस कर गया। तो अब क्या होगा?
तो देखना पड़ेगा, एक्चुअली एग्जाम वाला जो पार्ट है ना, वो आई एम
जी।
नॉट लुकिंग इनटू इट, बट अभी एक मेल भी आया, शायद कुछ डेट उन्होंने एक्सटेंड की है।
हाँ, वो तो जो असाइनमेंट हो चुके हैं मैं उनकी बात कर रहा हूँ, जिसकी
अच्छा,
डेट
जो
निकल गई जिसको।
ओके ओके ओके। सो लाइक योर जो तुम्हारा क्राइटेरिया है एग्जाम वाला सर्टिफिकेट का, उसमें कितने असाइनमेंट लिखे हैं? सभी असाइनमेंट लिखे हैं या कुछ 30%, 40 या 50% कुछ ऐसा लिखा है?
वो आई हैवंट गॉन टू दैट, आई हैव टू
ओके
सी
ओके।
दैट।
एक बार वो चेक करो पहले, उसके बाद लेट्स सी क्या होता है।
ठीक है ठीक है।
हाँ।
ओके। किसी को ईमेल तो नहीं करना पड़ेगा मुझे इसके लिए?
नहीं नहीं, पहले एक बार ये क्राइटेरिया देख लो, अगर उसमें लिखा हो कि 50% एटलीस्ट, तो फिर नो प्रॉब्लम ना।
ठीक है।
हाँ।
ठीक है, ओके, थैंक यू।
Sir, today we will discuss week 4 assignment questions
नो नो,
or
वीक 3।
week 3.
यस।
Uh,
ओके, आई थिंक वी शुड स्टार्ट। सो टुडे आई एम गोइंग टू टेक वीक 3 असाइनमेंट्स। सो आई थिंक you must aware about that, like we are discussing these assignments in three parts, like there are three persons which are discussing these assignments. So first part I am discussing, second part is taken by another person, and third part is taken by another person. So we have classes on like Friday, Saturday and Monday. So this is the course of Solar Photovoltaics, Principal Technology and Materials, taken by Professor Ashish Garg from IIT Kanpur, and I am Ravi Kumar, a PMRF Research Scholar at IIT Bombay. So let's start. So we were talking about the resistivity, resistance and conductivity from the starting first class. Like resistivity or conductivity of semiconductor lies where it is more, less, or some like in, or it is like in between of metal or conductor or insulators. So how do we measure this resistivity in case of semiconductor? Do you have any idea? Like simply how do you measure the conductivity or resistivity of a resistance of a conductor? Anything else? Like if we have a metal, or like we say this is a material which is made of metal A, and we want to know the resistivity of this material. So how do we go do about it? Simple physics, Ohm's law.
Yes, sir.
Yeah. So using Ohm's law, we will get R equals to V by I. We will just connect here voltmeter, or like we are just supplying voltage and we are measuring current here. So we are getting V and I, and using this VI we are calculating R, resistance, and from this resistance we know R equals to rho L by A, and using this we can calculate this resistivity for a metal. But in case of like here, what is happening? It is metal here, and these wire are also metals, so they are connecting with good connections. Like there is no, or there is very less contact resistance here. So here the resistivity value is somewhat real value. But what happens in case of a semiconductor? We have a large problem is there, large contact resistance. So what method we apply? Any idea?
Apply two probe method.
Yeah, 4 probe method.
Four.
This is 2 probe, like we can say this is 2 probe, and for the 4 probe method, what we do? We use 4 different probes, 2 for voltage and 2 for current. 4 probe method, 2 probe is this one, like, and here this is a picture of 4 probe method, and based on this structure here, there comes a formula which equals to R. How can we calculate? You can see, you can find it anywhere. So if this surface is changing, like if it is semi-spherical, then formula will be different, but this is the method by which we calculate the resistivity of semiconductors. Now we will move to the generation of charge carriers. What happens? Generation of charge carriers, how charges are being generated inside a semiconductor device. So, but have you like heard about this? Matter cannot be created, not destroyed, right? Then
Yes.
how we are generating charge carriers? Also, it is charge carriers. Are we really generating charge carriers? Are we really generating electrons? It is like electron is a, what is electron? Matter. It is a particle. So is it possible to generate an electron? It is generation, then it is right, and this does not apply for the generation part. Why? We are just like an whole pair and electron pair. This is a complete matter we are having. We are just separating them, and if it is like creating of charge carriers, then it won't happen. We can't create charge carriers. We can generate only. And how we are generating? We are generating a pair which is complementary to each other. Now I'll show some interesting things regarding this generation part only. So have you gone to the PV education website once, twice, or haven't gone through?
Can you repeat once more, please?
Sorry, which this? Wait a minute. What I was telling, generate or creating a material is not possible because
Yes.
matter cannot be created nor destroyed. So here what we are doing, we are generating electrons. We are not creating electrons, we are generating electrons. How we are generating? We are having a complete set, electron and hole. What we are doing, we are just separating them, which are complementary to each other. I hope this screen is visible to you, PV education website. Is it? Let me check.
Yes.
Yes. Yeah. So I was talking about generation of charge carriers. This is a very good website. Let's go to the generation. So how we generate a charge carriers? Just like what is your idea? In a like semiconductor, let's talk about this photovoltaic cell or semiconductor only. Using the light, how we are generating charge carriers? A light is going inside the semiconductor, and due to the energy of this light or photon energy, a pair of electron and hole is generating. So for this, we need to know the absorption of light. So first thing is that, see, this is an animation. I'll start it. What is it is showing? It is a semiconductor device. It is a valence band. This is a conduction band, and this is the energy band gap. So here what's happening? There are three cases. Photon energy is less than the energy band gap. What will happen in that case? See, photon energy is less than this energy band gap. So this energy is not able to move this like electron into the conduction band. And now let's move to the next. When this photon energy is more than this energy band gap, so now this is generating a pair. And what this is the like edge of this conduction band. Minimum energy required was that this one only. But what is happening here? This charge carrier is going for overshooting. So what will about this energy? This energy. So it will non-radiate this energy and it will come to the edge of the conduction band. So this was the second case. And excess energy is wasted here. And now let's see the third case. Third case is it is exactly equal. So here we can see this electron pair is generating and there is no wastage of energy. And the wastage in the previous part, like I'll show you again. So this is the photon energy is less than the energy band gap. No charge carrier generation. Now photon energy more than energy band gap. Electron hole pair generation, but it is having more energy So it will like lose this energy in the non-radiative form, which is known as thermal energy loss. And in the third case, it is exactly equal. So electron hole pair without no wastage of energy. So this is how the energy pair or charge carrier pair is generated, electron and hole. Let's move to the next part. There are some interesting these animations here. This is like absorption coefficient for different material. You can go through it. I want to show you something else. Yes. Okay. First, let's talk about this. Yes. We were talking about this energy generation. Now we have seen how energy is being generated. My screen is visible, right? Yes. Oh, it's fine. So, like this is a semiconductor lamp, or if energy is coming from this any source of sunlight, so what will happen? It will go to the depth on the deep in this material. So what do you think? Which we have this energy like low wavelength and high wavelength. Or high wavelength represented by which color in the your or in the visible spectrum? It is red. Red light is having longer wavelength. And for the low wavelength we have blue. So what this absorption coefficient represent? It represent how much depth a light can penetrate inside a material. So if light is coming, so if it is just penetrating until here and some energy is penetrating from and some energy is penetrating to this depth and some more is energy like penetrating till this depth. So we have A, B, C, and I'll give you three colors. Yeah, Malade, you can switch off your like mic. So I'm giving you three options: red, blue, and green. So which corresponds to A, B, C? You just need to assign the value of which A represent which color. If it is penetrating less depth and if it is penetrating more depth, so which color represents which one? A, B, C. What do you think? Which color will be absorbed till the depth, extreme depth? So in this case, what happens? The light having larger wavelength will go to the depth, and the light having shorter wavelength will be die out on the surface. Same thing, I'll show you. Let me check first. Yes. See, this is what I was talking about. There are two lights here, red and blue. So blue light is not going till the depth, but red light is going to the depth. So it is saying high energy blue light is absorbed near the surface. High energy means low wavelength, and low energy light such as red light is absorbed throughout the solar cell. It means it is high wavelength or large wavelength. So based on this wavelength absorption, we have a very nice phenomena around us which represents this absorption in real life. So do you remember it? Do you have any idea about that phenomena which is being around us naturally? Have you seen the sun during this early morning or the evening time? Yes, no?
Yes.
So how it is seen in the evening time or in the early morning time? Which color do you see more?
Red.
Red. Why? Do you have any idea? Because atmosphere is also like a material, and in the evening or in the early morning the distance between the sun and earth is maximum. So what happens, the light which is coming from the sun, all the short wavelength are absorbed but only red left out. That's why we are able to see red color in the evening or in the early morning. So this is the link. I am giving you this link. Even I'll add this link in the YouTube channel description also. You can go to this PV education again and you can watch those animations. Those are very interesting. Even you can visualize everything using those animations. So based on this, we have a question which says choose the correct regarding absorption coefficient in semiconductors. These are the options. So this question is asking very simple thing, like this absorption coefficient will be more for direct band gap or indirect band gap. You have like very fair idea about this direct band gap, indirect band gap. We have seen this in the previous lectures. So which absorption coefficient will be more? And one person asked me this question in the first class or second class. Okay, we will move step by step. First we will see what is this absorption coefficient, alpha. Alpha is the ratio of light absorbed divided by total light which is fell on the surface. And then second term is direct and indirect band gap. So this is a direct band gap. A, Malad is saying A, okay. This is direct band gap. And this is indirect band gap. So Malad is saying absorption coefficient will be more for direct band gap and it will be less for indirect band gap. you can easily look into it. If light is coming this from here and same light is coming from here, and here are some charge carriers, so which one is easy? These charge to move these charge carriers just at a height or just change the energy, or for these charge carriers to move in diagonal or change energy as well as momentum. So which one is easy for the charge carriers? Yes, direct ones means only change in energy by conserving the momentum. So this one is easy rather than this. So that's why more light will be absorbed here, while light absorption here will be low. And then just now let's see the options. Direct band gap absorption coefficient will be more than the indirect band gap. Yes, this is the answer. Malade is right. Option correct answer is A. Let me open the chat. Okay. Now we are moving to the next part, which is recombinations in semiconductors. What is this recombination? We have seen the generation of charge carriers just now. Light is coming, it is absorbing inside the material or semiconductor, and due to this light energy or photon energy, charge carriers or pair of charge carriers is being generated. That is the generation of charge carriers in semiconductor. Now we are looking another aspect, that is recombination in semiconductors. What is this recombination? What do you understand by the word recombination? Any idea?
Make it recombine with the whole.
Yes, it is just opposite to the generation of charge carriers. In the generation of charge carriers, we are generating electron and hole pair. And in the recombination of charge carriers, what we are doing, we are like both hole and electron are coming together and they are recombining.
Yes.
Yeah. So how many types of recombination do you know?
Band to band, RG, cell level, Gaussian.
Okay, that's correct. That those three are the major one. Band to band, or like we can say this one, red hole recombination, and this is ozone. Yes. Now we will see some animations related to this recombination. We are just having an idea how this recombination is happening. We are saying theoretically electron and hole pair are coming together and they are fusing in one another. Now let's see what happens in a semiconductor actually. Okay, Malade is saying he has seen that. That's great. I am also showing you from the same website. Recombination, yes, this is the part we are talking about. So types of recombination here. So radiative, Ozer, and defect assisted, that with red hole combination as well, we have know that. So this is described using this animation. Here what we are seeing, this is the valence band, this is the conduction band, and now let's see what it will show us. We are just starting it. So this is band to band recombination. What happening? a charge carriers from here, it is coming to this another band, means from conduction band to the valence band, and it is combining with the hole, and an energy is being radiated. So it comes under the radiative recombination. Now let's see the next part, which is defect assisted recombinations, which is we also know red hole recombination, we have seen that. So what happens, there is a defect here, or we can say trap assisted recombination, there is a trap here. So let's start this. What happening here, an electron is coming from conduction band to this trap, and then it is resting here, and after some time it is going to the recombine with the hole. Now my question is, what is the difference between band to band recombination and this trap assisted recombination? At the end it is meeting with the hole only. So what is the difference actually? Just see this animation again. And so now let's see the third one also, Auger recombination. What happens here, an electron recombine with the hole and give its energy to second, pushing it to the higher. What happen, an electron from here, it is coming to the down and it is recombining with the hole, and the energy which is radiating from here, it is giving to this another electron in the conduction band, and it is moving at higher energy level, and from this level it is radiating this energy back, and it is coming to the edge of this conduction band. So this is the Auger recombination. So I was asking the difference between this one, see this one, and this one. Answer lies there only. What is the difference between these two recombinations? Ultimately an electron from here is coming to this valence band. Then what is the difference? Think. Here you can calculate diffusion length and all. Think about that. That you will read in the few next classes. See, here you will see a light coming here. See, this is the light. And is there any light here? See, no light here. So that's the difference. So the before one, band to band one, was the radiative recombination, and it is non-radiative recombination. And I'll tell you how. Wait a minute. Yes. So what happening, what is E equals to Hc by lambda? Do you know this? Do you have any idea about this? Hc equals to Hc by lambda.
Yes.
And this E is depending on
Material.
as well, or and here it is directly proportional to band or gap at which an electron is coming from higher level to the lower level. So we can say the difference between levels. So in case of this band to band recombination, this is the energy which is very high because it is large level change. This distance is large. So that's why energy is high. So Hc lambda. Lambda will be low. And lambda will be low. And we can say, if this is the Vibgyor thing, violet, we can say lambda is low for blue and lambda is high for red and heat. What is this heat? Which radiation is that heat? It is IR, infrared radiation. So here it is not radiating any radiation, rather than it is coming or it is radiating non-radiative energy, that is known as thermal energy. Thermal energy.
Sir, Sat told me heat as well as release of phonon.
Yeah, repeat.
Sir, Sat told me heat energy is radiated in trap energy and also release of phonons. Phonons, sir.
Phonons, okay. You are talking about this or something else?
Trap assistance. Trap assistance.
Trap assisted, okay.
Sir told me there is a heat radiated and also release of phonons.
Yes. Yes, not photons, phonons.
Phonons, sir.
Yes. So this is about this recombinations in charge carriers. Now these are the questions based on this recombination only. So first question says, which type of recombination process is most likely to take place in heavily doped semiconductor? And these are the options. Heavily doped semiconductor. Any idea? Is it non-radiative recombinations, Oza recombinations, SRH, Shockley red hole recombination, or band-to-band recombination?
Sir,
Okay.
non-radiative, sir.
Non-radiative, no. See this one. What happens in Oza recombinations?
Okay.
Electron falls from conduction band to valence band, yes, to recombine, and energy released in the, yes, third carriers. So here you can see heavily doping leads to the Oza recombinations, because we have a formula which says this tau in Oza will be inversely proportional to Na. Na is the concentration
Concentration. Acceptor concentration.
doping. So here it will be the Oza recombinations. Have you seen this lecture or not?
Yes, sir. Forgot. Lots of lecture is coming.
Okay. Okay. So in the last class we also have seen this drift and diffusion. Where it happens? It happens, just tell me if this is a conduction band and if this is valence band. There are three parts, A, B and C. This drift and diffusion happening in which place, A, B or C?
Sir, B position.
B position.
Because sir, suppose charge gradient, one side is moving from one side to another side. Okay, from the depletion region.
Is there any charge carriers which is always present here?
No, sir.
Then how diffusion can take place here? Because diffusion move from higher concentration to the lower concentration.
Yes, I have to do.
Yes.
Concentrate.
Yes.
Sir, it may be A or C.
Yes.
Because
Yes. It is A
any-
and C
any-
only. It is A and C only, not B. Drift and diffusions.
So Ravi, still this is not a core subject, so I'm unable to respond to you particular. So
Wait, your voice is breaking in between. Can you come again? Yes, Rajiv?
I just want to convey that this is not my core subject.
Okay.
So I am unable to respond. It's a learning for me, so please bear with.
Yes. No worry. If you are not getting any concept, you can ask again. It's okay.
Okay, sure.
So drift and diffusion, we have seen it, but once again, I would like someone to tell me. Just tell me the cause of this drift and cause of this diffusion, like force behind. Here though we have just talked about this concentration difference. And here it is external force, for example delta V potential difference. So when an electron is moving due to external force, then we will say it is drifting. And when an electron is moving without any external force, then we will say it is diffusing. Very nice animation. I'll show again. Sorry, Melody. I think you have seen those animations as well. Yes.
yes, sir. Yes.
Yeah. But those
Sorry, last lecture, you tell me a body spray
yes.
example for diffusion and drift.
Yes.
While
So I am talking about carrier transport. So this is the carrier movement in the semiconductor. Let's see, this is a scattering of atoms, how it moves. Electron move in the random direction until it is scattered off a defect or lattice atom. It's like it is bombarding with the nearby atoms and it is having a random motion. See, carrier in semiconductor are in constant random motion. There is no net motion of carrier unless there is concentration gradient. Concentration gradient means diffusion, or an electric field means drift. So these charge carriers are in random motion until there is concentration gradient or an electric field. So let's see this random motion of this electron or charge carriers. This is the random motion. Now we will see, this is the random motion. Now we will see first part. First part says concentration gradient. So now let's see what happened due to concentration gradient, but that is known as diffusion. these are the carriers. It is just showing like how this diffuse. Some particles are moving that left side, some are moving to the right side, because the probability of movement is equal for the both side. Same thing, same thing. Yeah. So it is just saying diffusion in the random scattering of carriers to produce a uniform distribution. It will be always uniform. And this one is that diffusion one. This is a random motion. It is reflecting from any point because of bombarding with the atoms. Now let's see. Now we have some holes in the blue color and electrons in the red color, and these are the like electrons, these are the holes, and they are diffusing into each others. See, all the red electrons were at one place and all the blue one were at one place, but due to diffusions, due to difference in the concentration, they are mixed now. This is due to diffusion, and this is the random, or this is the normal distribution. For the basic thing, we don't need to know all about these things. This is just mathematics about the random distribution. Now we will see the drift. Now we will see the charge carriers in the presence of electric field, and there should be a net movement. Like, see, no electric field, no net movement. It is a random movement, but no net movement. It is started here and it came back here only, so no net movement. But in this case, there is an electric field represented by this color, and now let's see what happens. So in presence of electric field, there is a movement. It is a bombarding movement only, but due to presence of this electric field, there is a net movement as well. It is coming back here at the same place. Starting point and ending point is same for this electron, while this electron started from here and it is now here. Why? Because of electric field. This is also an interesting one. So these are the electron and hole. No electric field, so no net movement. But here we can see electric field action is positive to negative. So electron will be attracted to the positive side and hole will be attracted to the negative side. So there is a net movement. Electron are moving from this like towards this positive charge, and hole are moving towards the negative charge. And these, there is no electric field, so no net movement here. Once again we can see this is the hole. It is going towards the, like, it is positive to negative, so it is going to the negative side, and this electron is going towards this positive side. One more animations. See, this is the random movement. There is no electric field, so electron and holes are in random motion. Now we will start the electric field. Electric field is on. Now you can see the holes are moving towards negative side and electrons are moving towards the positive side. Now we will just switch off this electric field. Now again this is the random motion and start electric field. Then it is a net movement. This is called the drift. Same thing here, no equation. And that's it for this animations. Yes, we are back. So now I think you have got the idea about drift and diffusion. And this is the link. I'll add this link in the YouTube description as well. Now let's see the question based on this drift and diffusion. Question is very easy and you need to answer it. The drift current in semiconductor is due to. Just pay attention. It is saying drift current. And these are the options. Is it due to concentration gradient, diffusion of charge carriers, applied electric field, or rise in temperature? Just seen this in the animation. A, B, C, or D? I am waiting. This is the easy one. Even we have seen it few seconds before. I told you two things: drift, diffusion. It is due to electric field. Yes, yes, Rajiv, you are right. C, electric field, and this is concentration difference. So here it is applied electric field. Yes, answer is C. Second question, next question, the electron diffusion current in a semiconductor is due to electric field defects, carrier concentration gradient, both carrier concentration gradient and electric field. C again. Yes, great. Carrier concentration gradient. C. So now we have seen this, the transport of charge carriers in valence band and conduction band. Now we will move to the next part. Okay, one more question about the carrier lifetime. So carrier lifetime in a semiconductor increases with and these are the options. Do you have any idea about this carrier lifetime? And it is a multiple answer question, MSQ. See, we have two things. One is diffusion length and another is carrier lifetime. We can say carrier lifetime is the time before the recombination. Rajiv Gani is saying B and C. Okay, I'll see. And diffusion length is the length or distance it moves before the recombination. We will go one by one. It is saying increasing trap density. It is saying carrier lifetime increases with if there will be more trap density, so recombination will be more or less?
Sir, more, sir.
More. So A can't be answer here, because
No, sir.
now if A is not correct, then B is correct, because it is just opposite.
Yes,
So
sir.
decreasing the trap density will increase the carrier lifetime, or will decrease the recombinations, which will increase the carrier lifetime. Now the C1, it is saying increasing donor concentration. In the previous question, we have seen highly doped semiconductor devices having which kind of recombination more?
Roger.
Ozer. So it is saying due to donor concentration, recombination increases. So if recombination is increasing, then the lifetime will decrease or increase?
Sir, decrease, sir.
It will decrease. So this cannot be an answer. Then
B
answer
and D.
B and D. Yes, B and D.
Sir, there is a mathematical formula is there, na?
Yeah,
Carrier
mathematical
lifetime.
is there, but see, I believe in physical understanding. If you know the
Yes, sir,
understanding,
definitely.
if you know what is happening really inside a device, then you won't face any trouble anywhere, in any subject, in any questions. If you know the basic and you will just go with the basic, then you will solve each and every question. Because sometimes what happens, we forget, like let's say a simple question like V by I. Sometimes we think it is I by V, it is something else. So in this mathematical thing, we forget we know the notation, we know the abbreviations, we know the like which symbol is there, but sometimes we place them in different order. So from the basics, it is like B and D is the answer here.
Thank you, sir.
Yes. Now let's move to the next questions, and which is the measurement of mobility. Do you know how a mobility is measured? Which method? Very famous method. For the mobility measurement, we have a very famous method and very famous effect. Just think. Think about it. Have you heard about Hall effect?
Yes, sir. Yes, sir. Hall effect.
Yes. This is the Hall effect or Hall measurement. What we can measure in semiconductor using this Hall measurement based on the Hall effect? Give me two things at least.
Sir, mobility and type of
Yes. Type of
mobility first
semiconductor.
and semiconductor
Yes. Type of semiconductor and mobility.
mobility.
Yes. Using this Hall measurement, we can measure this type of semiconductor and mobility. Do you have any idea how type of semiconductor we came to know using this method? Any rough idea?
No, sir. I was going.
No idea. Okay.
No,
Today
sir.
you will get an idea. See, first let's understand what is this Hall effect. First, we will read it. The Hall effect is the production of potential difference. across an electrical conductor that is transverse, means perpendicular to an electric current in the conductor and to an applied magnetic field perpendicular to the current. It was discovered admin hall, leave it. So here just see this is an animation. I hope you are able to see this. This is the voltage, and
Yes.
when this magnetic field is being applied, you are able to see there is a voltmeter, and there is in, like, it is showing some value of this voltage. It is changing with the magnetic field. So whole effect is the simplest thing. It is just saying, it is based on the Lorentz principle only. It is saying if in a like element or in a electrical conductor, if current is passing and that conductor is placed in the magnetic field, then there will be a potential difference. Okay, so now we will see the first part. Second part, we just get an equation, and using the equation we can calculate the mobility. We will see the first part qualitatively, how we came to know or how we will get the semiconductor is p-type or n-type. See, this is the whole effect in n-type semiconductor. This is the p-type. I'll describe both at once. You just need to tell me one thing. What is the difference between p-type semiconductor and n-type semiconductor? Basic difference.
So P-type majority carrier holes, minority carrier electrons, and N-type semiconductor majority carrier electrons and minority carrier holes.
Yes, okay. Let's talk about based on the charge only. So in the n-type we will have negative charge more.
Yes.
In the p-type we will have
Negative, positive.
positive charge more. And if a charge carrier is moving in an electric field and in the magnetic field, it will have some force. A force will be applied on this.
Yes.
So due to this force, it will move in a particular direction. So what happens? In a magnetic field, a perpendicular force is applied. You must know, like, I don't remember the which principle is that, right hand rule and thumb rule.
Fleming.
Yes. So based
Fleming.
on that we can get the direction of force. Direction of force we can get it. So just see, if this is a semiconductor and this is also semiconductor, and the charges here are forced to settle in the bottom surface, and same thing is happening with this another semiconductor. So in the bottom surface you will have different charge for different type of semiconductor. Yes or no?
Yes, sir.
Because force is in the same direction, it is applied on the particles, and those particles are having different charge, so accumulation of charge will change the polarity on the bottom surface. So in case of n-type semiconductor, the bottom surface will be negatively charged. In case of a p-type semiconductor, the bottom surface will be positively charged. So by measuring the polarity of the bottom surface, we can get an idea about whether a semiconductor is p-type or n-type. I hope you got an idea. Just fair idea,
Yes,
you
sir.
should know.
Yes, sir.
Yes. Okay, so next question based on this whole measurement only. and these are the options. It is saying which of the following parameter can be determined from the whole measurement. D, so we have seen the mobility, and other, it is multiple question type. C, we have seen this charge carrier types, P type or N type. Okay, just think about it. If we have a surface and we are getting all the charge particles on this surface, and we know the charge carriers, number of charge carriers n, and we know the like geometry of this surface, can we get density? Yes, density we can get. And yes, a also. Can we get lifetime? No, here we are not talking about any kind of recombination or any method which is measuring the diffusion length or drift length or like carrier lifetime. So no, we can't measure the lifetime of charge carrier using Hall measurement. So answer is A, C and D. Now next question, which is a numerical one, which is saying when an electric field 12 volt per centimeter is applied across a semiconductor at a certain temperature, the average drift velocity is 75 meter per second. You need to calculate the electron mobility in centimeter square per volt second. These are the options. This is the power. If you know the formula, just calculate it. If you don't know the formula, just let me know. Here only two quantities given. What is given? Electric field 12 volt per centimeter and drift velocity Vd equals to 75 meter per second. Okay, one famous and very simple question. You are having wiring in your house. So what is the speed of those electrons moving through this wire? You just switch on your light and you see light start like shining within microseconds. And you know the electricity is the flow of electrons. So what do you think about the speed of those electrons inside these conductors? Are you getting the question? Are you getting the question? See, if this is a table lamp and I'm just switching it off, and I'll just click here and it starts, and there are some electrons which are moving from here to here. So I'm just asking the speed of those electrons. Do you any idea? What do you think? It is equal to speed of light. It is equal to some 1000 km per second. What is your thinking about this? Any rough estimate based on your understanding? There is, I'm not saying some you should know, some you should tell me the correct answer. No, it is just a like problem around us, which is very interesting. It is not a problem, it is a phenomena. It's any rough estimate what do you think?
Distance travel by time, millisecond, how many distance electron travel, this is the speed.
Yes, yes. What is the value you are telling?
Distance, distance travel,
Yes.
electron distance travel in how many second, millisecond, this is the velocity.
Yeah. But what do you think? You are saying the theoretical part. I'm asking in numerical value. What do you think with this distance per unit second? That is the thing I'm asking. Light, your light is electricity. I'm not saying light because sometimes we confuse with this light and electricity. Your electricity is coming from the any dam or any coal power plant, and if they start electricity point there, you get electricity in your house. So with how in how much time you get the electricity? Or some another way we can understand, take a wire of 100 meter and just plug one side and bulb, and another side just connected with the plug or in the electricity point. So how much time it will take between the putting the wire in the switchboard and lighting up the bulb?
So the distance travel and the flow of electron.
Yeah.
Time required to travel the distance of electron.
Yes, yes, but have you done these all, or have you seen these things around you? You are saying right thing. You are saying the electron, how much it will move in per second, but I'm asking the same thing. How much it will move in 1 second? What is your idea? How much distance it will move? It's okay if you don't know. It's fine. This is not a bookish question. It is a question around like from the our surroundings only. And any person, any child can ask this question from you, because whenever a child study about this, electricity is a flow of electrons, then this thing can come in his or her mind. If it is the flow of electron, then what should be the speed of electron? I think even you can calculate it. Let me try this. If we have okay, I'm just telling the answer. It is few millimeter per second. This is the speed of electron in a conductor. Okay, now let's do this question. You know the formula? Okay, I'm giving you the formula. This is the formula. Our drift velocity will be equals to mu e. This is given and this is given. You need to calculate mu. Very simple. Mu equals to Vd upon E. So answer will be. Now though you can calculate na. What is the answer? What is the answer? Should I calculate it? It is 75. Just convert it into centimeter per second. Centimeter per second. Divide by 12 volt per centimeter. And
Option C.
yes. Option C. 6.25 into 10 raised to the power 2. Yes. Option C is the correct answer here. Next question, which is very similar, same thing. When an electric field of intensity 15 volt per centimeter square applied at a certain temperature, the average drift velocity is 71 meter per second. You need to calculate electron mobility. Give me an answer within 2 or 3 seconds.
Say D.
D. Yes. 4.73 10 raised to the power 2 D. These are the powers. D is the correct answer. Yes. Now let's move to the next question. Which of the following is the reason for band bending observed in semiconductor material? And these are the options. A. Presence of electric field. Yes. A is the correct answer. Electric field. A. Okay, we have completed this. Now I'll ask you a question, very simple one. See, this this is a wire and a bulb is connected here. This is 1,000 km long wire, and here you are applying electricity. Don't confuse with electricity. And same thing, this is the wire of 10 meter long. So you just need to tell me the time, delta t and delta t. You just switch on here. Let's say at 7:00:00 p.m. and 7:00:00 p.m. You connected these circuits. So this bulb will light up at what time? After how much time? How much delay will be there and how much delay will be there? Okay, for this I'm telling you an electron is moving 1 centimeter per second. Now let me know. An electron is moving 1 centimeter per second. Question is clear?
Yes, sir.
Okay.
Sir, both are doing same kind, sir.
How much? What is delta T?
Because almost electron is there, na, sir. So when I switched on, circuit is complete, sir.
Sorry. Come again.
Sir, when I switch on the light, sir, circuit is complete. So both are doing same kind, sir.
Yeah, but electron is moving at 1 centimeter per second. Even it is the speed of electron is very less than this 1 centimeter square per second. Then why there is no time lag? This is just basic understanding question.
Yes, sir. Sir,
Yes.
electron speed is very heavy,
Yeah.
sir. 2000, I think 2000 kilometer per second.
2000 kilometer per second. I'll show you the speed of electron. Just check it. What is written there? How much it is?
0.2 centimeter per second.
And you are telling me 2000 kilometer per second. This is the about home wiring which I am talking about. Now what do you think? Just think and discuss now. It's okay if you are not getting it. Just use your basic understanding. Basic, very basic. What is conductor? Getting something? No?
Sir, please tell us.
Okay. See, what is a conductor? If this is a conductor, this is full of electrons. And if it is full of electron like this, it is full of electrons. So electron that we are pushing here is not actually moving here at an instant. It will take time. It will move eventually there, but it will definitely take time. But our bulb is start working as soon as we just put an electron here, then electron start coming out from there. It is like an pencil you have seen na? If we just have like we just remove the things from front one and then we just put it from the behind. It is just like that only. An conductor is full of electron. If one electron is we are inserting from one end, then the electron which is already available at another end will come out. That's why there is no lag between this electricity, even it is 10 meter long wire or even it is 1000 meter long wire, kilometer long wire. Doesn't matter, the delta T will be 0 only. But the electron which inserted here, definitely it will take time to move here. But it doesn't matter, we are getting electricity or our devices start working as an instant electron goes inside an conductor. Got it? Any confusion?
No, sir.
Clear?
Yes, sir. Yes, sir.
Okay. This thing is very interesting
Yes, sir.
actually. People
Yes,
say the electron moves with the speed of light. That's why there is no lag. But that is not correct.
Yes. A millisecond is there.
Yes.
Yes, sir. Yes, sir. Previous lecture you tell me that some questions you had. I have some doubts. Some questions, assignment questions. You told me that we had.
Okay, like I have seen those questions 5, 6, 12 and 15. I can discuss directly from the web only.
Yes, sir.
So one question was about this dark current, right?
Yes, sir. Yes, sir.
Okay.
Answers already sir provided, but I don't.
I know. Wait a minute. See, question. Yeah. Question was 15, 12, 6 and 5, right?
Yes, sir.
So in case of 15, it is just the equation. We just have an equation of semiconductor or diode. I equals to exponential minus EZ by KBT. So it is just asking the proportionality constant. How it is proportional. So current or current density doesn't matter.
Okay.
So Eg by kBt, you already know this, right?
Yes. Yes, sir. Yes.
And then it was 12.1.
The 12, I want to know the formula. If a two is there,
Yes. What
so
is
what
the
is the formula?
issue here?
Sir, where two resistance is there, I want the EV formula, sir. I want to know only the formula.
The registration of the integer semiconductor is 4.5.
Sir, zoom it, I just note down the formula.
Okay. This thing.
Okay, sir.
And then we had which one?
12,
6.
5.
6 and 5. See,
Yes.
5 is all about dark current, and this is Shockley-Radon recombination dark current. This is diffusion assisted dark current. And have you completed this dark current in the lectures? Not yet, na?
Yes, sir. Yes, sir. Just PN junction set to some dark current.
Okay. So I'll take this question with those like next week only. I can tell you the dark current, why this is dark current. So what happens? There are different kind of dark current. Sometimes these recombinations are happening, which is the SCR. Those create dark current, which is known as SCR dark current. And some diffusion assisted means I just told you what is the diffusion. And if this diffusion is causing any current, this question I'll take in detail because I'll tell you about more about dark current and different kind of dark current in the like forward bias and like backward bias or reverse bias. And the other question was that this 6-1 for the carrier
Yes,
mobility in a no degenerative semiconductor, it decreases with decreasing temperature. What is the carrier mobility?
Mu.
Mu. What is the unit of this mu? It is meter per.
Centimeter square by volt.
Okay. Even we just
Centimeter square.
mobility, you just think about this is a movement of electron or movement of any charge particles. So what happening? It is asking the mobility relation with temperature and doping. Now tell me, if there is increase in temperature, then bombarding of the charge carrier will increase or decrease?
Sir, increase, sir.
Bombarding will increase, then the net moment of charge carrier will
also decrease, sir.
decrease. So that's why it increase with increased temperature. Second thing, with the high doping, what happens? Number of charge carrier increases. Same
Yes,
thing
sir.
if number
Momentum decrease.
Yes.
Momentum decrease.
And in the D1 it is saying relatively constant for low doping concentrations.
Okay, sir. Sir, one thing, sir. Assignment one last question, sir. 15.
Wait a minute. 15 though I think have been taken by another TA. You haven't watched the lectures?
Actually, I was in duty that time. That's why.
Okay. I have to see which
15.
question you are talking about. Assignment 1?
15. Last question, sir.
Okay. Yes. It is asking maximum day length on April 12, 2023 in Kanpur, located at latitude and longitude. It is asking the maximum day length.
The same formula I have used. I think some calculation I have missed it. That's all.
Okay, okay. You just take a
Okay,
snap
sir.
or you can rework
Yes, sir. I
on
just
that.
take. Okay, just take one snap of because same formula I have. Or
If you have used the same formula, then there may be some
same formula.
mistake within the
Calculation.
radian or degree conversion.
Yes, sir. That's why I'm asked.
Yeah, that's the biggest problem while we calculate this cos theta and cos inverse. We
Yes, sir.
forget to change our degree and radian.
Okay,
Yes. So keep in mind while
sir.
working on those kind of questions.
Okay, sir. Okay, sir.
Yes.
Thank you, sir.
Yeah. So yes, we are done with the today's lecture. Now I'll
Yes,
see
sir.
you in the next lecture, which will be next Friday.
Okay, sir. Thank you, sir.
Yeah. Okay.